So today we're going to start off with systems of equations. So basically what this is just equations where you have two or more equations and two or more variables in each equation. And when you have the same number of variables as equations, these are typically pretty easy to solve because you can simply use substitution or elimination in order to figure out how to isolate one variable and then get the answers from there. So this is probably going to be easy for some of you, but we're just going to do a quick review of simple systems of equations. So let's just start with this example. It's relatively simple. Also, please excuse my handwriting. I'm not used to writing with a stylus, so it's going to be kind of messy, but please bear with me. So we start off by saying that in this question, there's not a really easy way to eliminate x or y by themselves. I mean, isolate them such that you can get an expression where you substitute. You're going to end up with some messy fractions such as 117 over 15 or something like that when you try to isolate a variable. So instead, we're going to try to eliminate one of the two variables instead. So what looks easier here to eliminate is the variable x, because we can notice that 18 and 15, they have a LCM of 90, whereas if you try to eliminate the y variable, 17 and 4 don't really share any common factors that make it easy to eliminate. So we're going to go ahead and multiply the first equation by 5. This will give us the 90x. This is 885. And then we're going to go ahead and multiply the second equation by 6. Oh, Justin, did you record, by the way?
Yeah, it's recording.
Okay, great, thanks. So this is going to be 90x plus 24y is equal to 702. And we'll call this equation 3, call this equation 4. So right now we have two 90x's. The obvious thing to do is just equation 3 minus equation 4. Oops. And this will just give us 61y is equal to 183. So from here, we get that y is equal to 3. Now we just plug y back into either equation. I'll just plug it back into equation 1. So we get that 18x is equal to 177 minus 17 times 3. So this is equal to 126. So then x is equal to 7. So we get our solution, y is equal to 3, x is equal to 7. That was simple enough. So what happens if we have more than two equations? Well, let's try a slightly harder example. Now we're going to have 3 equations. So the key to solving these is that you want to eliminate one variable from the equations until you get two equations of 2 variables each, which is back to what we had before, and that will make it really easy to solve. So the variable that's probably the easiest to eliminate here would be y or z, since 2 of them are the same. I'm just going to go for z. So we can start by adding equations 3 and 5. And this will give us 8x plus 8y. You notice that the z cancels. This is equal to, oops, I think we have a typo. This is supposed to be a -1. That's supposed to be a -1. Yeah, that's how I set it up, my bad. So we get that ax plus 8y is equal to 25 minus 1 is 24. And so then when you divide the entire equation by 8, you get that x plus y is equal to 3. And then we can also eliminate the z variable by adding 6 times equation 5. And then we add that to equation 4. That gives us 6z term, which will cancel out with the 6z in equation 4. So when we add these two, I'll go ahead and write it out so not to skip any steps. So 6 times equation 5 is 30x plus 12y plus 6c, 150. And then equation 4 is x minus 2y minus 6z is equal to 6. So when you add these two, you get 31x plus 10y, and the z's cancels, and this is equal to 156. Now, let's move over a bit. Okay, now we have these two equations, this one and this one. We can just write here, we can move one of the variables to the other side in order to isolate one of them. So we can say, for example, x is equal to 3 minus y. And then we'll plug this back into this equation. We'll get, I'll go up here, 31, 3 minus y minus plus 10y is equal to 156. So this will give us 96 minus 31y plus 10y is equal to 156. And this will give us negative 21y is equal to 63. And therefore y will just equal negative 3. Now, if we plug this back into this equation, we get that x is equal to 6. Oh my God. And then we can plug both of these values in back to any of the original 3 equations here. Let's plug it into equation 5, for example. So we get that z is equal to 25 minus 5 times x, which is 6. And we subtract 2 times y as well, which is negative 3. And this will give us z is equal to 1. So our final solution would be 6, negative 3, 1 for x, y, z. Hopefully that was pretty straightforward. So these types of equations, again, they're not that hard since we have the number of equations equal to the number of variables and everything's explicitly given to us. But sometimes it's a little more obscure than that, as in the problem won't directly give us the equations. So we're going to have to try and figure them out ourselves. So this is where I'm going to introduce the concept of d equals RT. So if you're not familiar with it already, d equals RT, it's a very important equation, which the d represents the total amount of work that is being done by something or a group over amount of time, where r represents the rate at which this group or one person works, and t is the total amount of time that the work is being done. So this might seem a bit unclear at first, but I'll show an example later, or I can just show one right now. So for example, if someone runs at 6 miles an hour, 6 miles per hour, and they run for 5 hours, well then this would just be the r, this would be the t, so the distance that they run is equal to RT, which is equal to 30 miles. So that's just the basis of this equation, and you can obviously rearrange the equation as well if you divide both sides by t, or you divide both sides by r. You get these two as well, and they're basically the same thing, just rearranged. And you'll see that the concept behind them all is basically the same. So let's move on to an example for these. So this example, first of all, it's important to see why that this is a d equals RT problem. So first we notice that the problem, it gives us 2 different rates. One is this 30 miles per hour, and one is this 20 miles per hour. And there are 2 different rates at which she drives in different weather, one which is raining, one which is not raining. And then the problem also gives us a distance, the 16 miles, and also gives us a time, which is 40. So right already we have like distance, rate, time. So you can probably already see that this is going to be a problem which we have to use d equals RT. And the problem, so it asks us how many minutes does this Shelby drive in the rain. So we can assign that to a variable. Let's just say x. It's the minutes she drives in rain. And then since the problem splits the amount of time between, the driving conditions into raining and when it's not raining, we also need a variable y, which represents the amount of time she drives when it's not raining. Let's just say in the sun. So these two variables we're going to be using to form a system of equations in order to represent the scenario given in the problem. So using d equals rt, we can write that the total distance, d equals rt, the total distance is 16 miles. And we're going to have a sum of two different expressions. One which is going to represent the amount of time that she drives in the rain, and one's going to represent the amount of time, the distance she drives in the rain, and the other is going to represent the distance she drives when it's not raining. So the rate for when she's driving in the rain, the rate is 20 miles per hour. So we're going to write 20, and then the time is going to be, we assign that to the variable x, so it's 20x. And then the rate which she drives in the sun, it's given as 30 miles per hour. And the time she drives is going to be y. Or also, let me make a correction real quick. This x and y here, it's actually not minutes. We're going to actually have to represent these in hours. And the reason for that is because the problem gives us the speeds in 30 miles per hour instead of minutes. So we're going to have to convert the times from minutes to hours in order to properly have the times match up. So this is one equation. However, since we have two variables, x and y, we need another equation in order to solve it. So this equation is going to come from the total amount of time. So we see that the total amount of time she drives is 40 minutes. However, it doesn't specify how much of this is in the rain and how much of this is in the sun. So we can write an equation for it, which is just x plus y is equal to 2/3. And again, 2/3 is because 40 minutes is equal to 2/3 of an hour. And this equation represents the total amount of time she was driving. So now that we have this, we can just solve this system of equations. Let me move over here. Or I'll just move down. I think that's better. So we have these two equations. We can multiply the second equation by, well, since we're trying to find x, let's try to eliminate y. So let's multiply the second equation by 30, which will give us 30x plus 30y is equal to 20. And now we can take this equation and we can subtract the first equation from it. And this will just, to be clear, this is 3, this is 1. So equation 3 minus equation 1. And this will give us 10x. The y's are canceled, is equal to 4. X is equal to 2/5. And the problem asks us the total amount of time, the total number of minutes she drove in the rain, which is x. So therefore, if we convert this back to minutes times 60, this will just be 24. Okay, so that was an example of a pretty simple distance equals rate times time problem. As long as you understand the concept behind the equation and know when to apply it, the equations that come from it are usually pretty straightforward, and you can just solve them with the traditional methods we described in the previous section. So now let's try a slightly, not harder, but just a different type of example. And you see in this example, I'll give you a second to read it. Yeah, so basically this example, we see that we're given two different rates, 7 miles per hour and 12 miles per hour. However, we're not given a distance or a time really. So that could seem problematic at first. You might think, oh, well, how do we use d equals rt? And some people might even jump to the conclusion that the average speed is just 12 plus 7 over 2. This is wrong because the amount of time he spends going up and down is different. So therefore, we can't just take the direct average of the speeds like this. There's going to be an easy formula we can use, which I'll show you guys later to solve this, But first, let's understand sort of why that formula would work. So first, we have to realize that as for average speed, an average speed is equal to, write this out, is equal to the total distance that Jax runs over the total amount of time that Jack runs. So first we need to find the total distance, then we need to find the total time. But again, the total distance and total time are not really given to us. So how do we do this? Well, since the problem doesn't specify, and because of the fact that the distance going up the hill and the distance going down the hill is the exact same, it's the same hill. You're going to travel the same amount of distance up and down it. Therefore, we can just assign any number to this distance, and it won't really matter. The value is arbitrary. So we can just say the distance that he travels up the hill is 1 mile. And the distance that he travels down the hill is also 1 mile. So therefore, the total distance, which is this right here, this is just 2 miles. That's the total amount of time that this is the total distance that he'll traverse. Okay, so that's simple enough. Well, we'll also need to calculate the total amount of time. So in order to do that, this is where we take advantage of D equals RT. So let me actually move over here. So the problem states that he runs up the hill at 7 miles per hour. And using D equals RT, or more specifically, we can use T is equal to D over R. This is the time, which is basically just 1 mile, which is the distance he takes, which is the distance going up the hill, and then divided by the rate, which is 7 miles per hour. And therefore, the time that he spends going up the hill is just 1/7 of an hour. And we can do the same thing when he goes down the hill. T is equal to D over R, which is equal to 1 mile. And the 12 miles per hour. And that's going to be the rate. So therefore, the total amount of time he spends going down the hill is just 1/12. So we have the amount of time he goes up the hill, the amount of time he goes down the hill. The total time will just be the sum of those two. So total time, 1/7 plus 1/12. This is just 19/84. So now we just plug back in. Oops, I erased all that. Now let's plug back into this equation, the total distance over total time. So his average speed would just be 2 miles over the total time, which is what we said, 19/84. So his average speed would just be 168/19 miles per hour. And this value should come out to be somewhere between 7 and 12. And it's probably closer to 7 since he takes more time going up the hill. So it'll be a bit weighted towards the upward speed than the downward speed. And that's our final answer. So yeah, also said earlier that I would show you guys the formula, how to solve this quicker. So basically when you have something like this where the speed is arbitrary, or sorry, the distance is arbitrary, we can just use the harmonic mean formula, in which the harmonic mean basically is when you have two different values, A and B. The harmonic mean is just 2 times A times B over A plus B. And basically this is what we can use to plug in 7 and 12. So if we try that, this is just 2 times 7 times 12 is 168. And then 7 plus 12, oops. 7 plus 12 is equal to 19. And you see that this is the same answer as before. So that's just a quicker way to do this problem. But if you look at the reason why it works, it's basically the same thing. It derives from D equals RT. That's what I'm trying to say. So next, we can talk about a type of equation where it isn't really as easy to go about as d equals rt or any of the problems that we've talked about before. And the reason behind this is that we're gonna have to do a bit of casework here. And what I'm talking about are absolute value equations. An absolute value equation is basically an equation where you have, let me go down, where you have something like absolute value of x is equal to 6. And the reason that they're tricky is because this x can have two different values. X can either be 6 or it can be -6. And you're gonna have to try every single case in order to make sure that you find all the solutions. And even when you find all the solutions, it's really important to make sure that all of them work. Because when you have absolute value equations, you end up with a lot of extraneous solutions. And it's really important to also stay organized when you solve these problems, because you might have like a lot of absolute values in the equation, like the one we're about to see. And therefore you might have lots of cases like 2 times 2 times 2, which is like 8 different cases. So you're gonna have to be able to keep track of all of them and just make sure that you stay organized to don't like miss one of the cases. So let's take a look at this example. So basically here we see 3 different absolute value signs. We see one around the x, one around the y, and then we see one final absolute value around the absolute value of x minus the absolute value of y. And we have that. That means that we might have potentially 2 times 2 times 2, which is 8 different cases. And this seems really scary at first, but we can really cut this down a little bit in order to make it easier for us. So basically, we're gonna have something. Let's take this outer absolute value first. So if we considered outer absolute value, that means that the absolute value of x minus the absolute value of y, this can take on a value of 1, or it can take on a value of -1. Because if you take the absolute value of both of these, they're both going to equal 1. Then also, I forgot to mention, but we're going to ignore this first equation for now. Since it's pretty straightforward, we're going to use that later in order. Once we have all the cases, we're going to use that in order to solve for x and y. But we're going to ignore it for now. And we're just going to focus on the absolute value equation. So we have these two values for the absolute value of x minus the absolute value of y. So from here, we can also split this into more cases. So first, we can get that the x minus y is equal to 1. We can also get that x plus y is equal to 1. And this comes from this case right here. So this will split into both of these because the y can be plus or minus realistically, since we have an absolute value around it. And the x, we're just going to sort of not worry about that, since it's symmetric in that you can just divide by -1 to get the same case, but on the what we're going to tackle later over here. So we're just going to focus on the sign of y right now. And then from this case, the -1, this will give us another 2 cases, x minus y is equal to -1, and then x plus y is equal to -1. So now we have our 4 different cases. We can just tackle each of these individually with this equation I mentioned before, the x plus 3y is equal to 3. So let's move down the page a bit. So let's say let's number these 1, 2, 3, 4. Let's take equation 1. So equation 1 is x minus y is equal to 1. And then we also have x plus 3y is equal to, what was it? It was 3. So in order to solve this, we'll just subtract the second equation from the first. So this will give us 4y is equal to 2. And this just give us y is equal to 1/2. And then if we plug this into either equation, we should get that x equal to 3/2. So this is one of our potential solutions. And then again, once we get all 4 solutions, we're gonna check them in order to make sure they all work. Since again, we have the chance of encountering extraneous cases when dealing with absolute value equations. So for our second equation, we have x plus y is equal to 1. We also have x plus 3y is equal to 3. So again, we subtract the first equation from the second, and then we get 2y is equal to 2, y is equal to 1, and if x plus y is equal to 1 and y is equal to 1, that just means x is equal to 0. And so this is another potential solution that we have. Now let me move over here a bit. Our third case is x minus y is equal to 1. And then again, x plus 3y is equal to 3. This time, hold on. Oh yeah, this is -1, my bad. Okay, now when we subtract the equations, we're gonna get that 4y is equal to 4. So therefore we'd get that y is equal to 1. And if we plug this back in, we should get that x is equal to 0. And then our final potential solution is if we have x plus y is equal to -1, x plus 3y is equal to 3, and then we subtract the 2, then we're going to get 2y is equal to 4. This will give us y is equal to 2, and therefore x would be -3. So now we have all of these solutions. Let me zoom out a bit. And you'll notice that we actually have a repeat here, x equals 0, y equals 1, x equals 0, y equals 1. So we can just eliminate this case, for example. And now we go ahead, plug back in all of the cases to make sure they work. So let's say we plug 1/2, 3/2 in. Oops. 1/2, 3/2 in. If we plug that back into the original equation, so we get that 3/2 plus 3 times 1/2 is equal to 3. That's right. And then the absolute value equation, absolute value of 3/2 minus the absolute value of 1/2. The absolute value of that is equal to 1. So this is just 1. The absolute value of 1 is equal to 1. This is also right. So this one works. We can try the same thing for y equals 1 and x equals 0 here. So we can say that 0 plus 3y is 3. That's right. We also plug into the second equation. We get that 0, absolute value of 0 minus the absolute value of 1. The absolute value of this is equal to 1. So 0 minus 1 is just -1. You take the absolute value of that, and that gets us 1. So this is also correct. We move up over here. Y is equal to 2, x equals to -3. So if we plug this back in, -3 plus 2 times, or 3 times 2, this gives us 3, which is correct. And then into the second equation, the absolute value of -3 minus the absolute value of 2, the absolute value of the entire thing is equal to 1. So this is 3 minus 2, which is 1, and the absolute value of 1 is equal to 1, so this is right. So in the end, we have 3 solutions that work, and that's going to be 3/2, 3/2, 1/2. This is one of our solutions. Second one is 0, 1, and then the last one is -3, 2. So these are our 3 solutions. Okay, so that was a bit tedious, but we noticed that as long as we stay diligent and organize our work so that each case stays separate and we don't mix them up, we can simplify the absolute value equation into something which is a lot more manageable, such as like x minus y is equal to 1. And we can deal with that a lot easier than something that has 3 absolute value signs in it. So therefore, we were able to get these 3 equations without too much like hard thinking. It was just kind of tedious. So now we're gonna move on, and we're gonna talk about a type of equation that isn't necessarily as easy to solve again, it's kind of a common theme. It gets a bit harder as we go, but this type of equation, we're not going to have the same number of variables as equations. In fact, we're going to have less equations than the number of variables given to us. And this is a bit hard because this is a bit difficult because we're not going to be able to use our traditional algebraic tricks to give us like hard values such as 0, 1 that we have here. It's going to be of a bit more number theory flair, I guess. And because of this, we're going to have to use a lot more non-traditional methods to solve it. So I think this would be best explained with an example. So let's talk about this one. So this is the problem from an AMC a few years ago. I'll give you guys a bit to read it. Okay, so basically this problem you might want to start off by trying just a bunch of different cases and seeing what works. So like 300 minus 210 is equal to 90. That's one amount of debt that can be resolved. But we want to find the smallest. And you might realize that 30 would be the smallest value that you can get with like a bit of tinkering around. Oops, I dropped my pen. With a bit of tinkering around. But how do we really prove that? And in order to prove this, we're going to take advantage of a number theory identity, which is this one. It's called Bezout's or Bezout's. I don't know how to pronounce it actually. But what I do know is that it states for two integers a and b such that the greatest common denominator of the two integers is some number d, then we can find two integers x and y that satisfy this equation here. Ax plus by is equal to d. So if you can see, this problem like sort of reminds us of the other one because we have our two integers a and b, that's 210 and 300. And we want to find integers x and y that make the equation equal some small positive integer. So this could be like 30, for example, or 90. But what it's basically asking us is what values of x and y would make this possible? And x and y, it's important to note that these variables aren't necessarily representative of the amount of cows or the amount of cows or goats that pigs and goats that we have. It just represents the number that's being exchanged. Because obviously, if we have x is equal to -1, we can't really have -1 goats, but this just means that one goat is being exchanged in one direction or another. So basically, using this principle, we get that the GCD of 210 and 300, GCD of 210, 300, this is equal to 30. And in fact, it's like, I guess not a corollary, but like a part of Bezout's that states that, in fact, every number that you can form as a result of ax plus by has to be divisible by this d. D divides all ax plus by. So this would make the next problem a bit easy for us, because this means that every possible amount of debt that can be resolved has to be divisible by the greatest common denominator of 210 and 300, which is 30. So therefore, we get that it's the only positive, or rather the smallest positive multiple of 30 is just 30. So this is just our answer. So that might seem a little abrupt, but that's the way that these type of problems work, because we can't exactly find x and y, or because we're only given one equation. it's not like our traditional type of algebraic manipulations. So here we're gonna have to use other forms to solve the problem. And here we take advantage of this identity, which tells us that the amount of debt that can be resolved has to be a multiple of 30. And therefore the answer, which is the smallest positive debt has to be 30 as well. And then this is a pretty, I guess, simple version of a Diophantine equation. So in which Diophantine equations, I'm not sure if I explained it, but basically they're equations that the solutions are integers and that they have typically less variables or less equations than variables. So we're going to move on to probably a Diophantine equation that you guys are more familiar with if you've encountered it before. That's going to be equations involving Simon's favorite factoring trick. So if you haven't heard of this before, that's okay. I know that AOPS likes teaching it a lot in their classes, and they have a valid reason. It's really useful. So let's try this example right here. This example states that we want to find all positive integers x and y that satisfy this equation. So again, we notice that there's less equations than variables here. We only have one equation, but two variables, x and y. So how do we find values for them? So that's where we're going to take advantage of Simon's favorite factoring trick. And I'll explain it as I go along in this problem, since it's sort of hard to encapsulate without a proper example. So in order to solve this problem, we start off by noticing that there's a lot of fractions, and we probably want to get rid of them. So we're going to multiply the entire equation, or rather both sides, the left and right hand side, by 9xy. And we do this to get rid of the fractions. So therefore, if we multiply the left hand side by 9xy, we get 9xy over x plus 9xy over y is equal to 9xy over 9. So this will just, once we simplify, the x's would cancel, the y is canceled, the 9 is canceled. We get that 9x plus 9y is equal to 9xy. And then we can move the x and y to one side in order to make it easier for us to factor. 9xy minus 9x minus 9y is equal to 0. Or sorry, not 9xy, just xy. The 9's got canceled. Or I think it's better to just do this. And the reason that we like this form is because we notice that the first two terms, the xy and the negative 9x, they both share x in common. So therefore, let's factor out this x from the first two terms. So if we factor out the x, we get that x times y minus 9. It's a bit messy. Rewrite that. 9 minus 9y is equal to 0. So now, in order to take advantage of this x minus 9 that we have here, we're going to try and factor out a y minus 9 from the second term. So in order to do this, we see that the negative 9y already has a y in it. So that means we just need a negative 9 to go with it. So we're going to add negative 9 times negative 9 to both sides. And if this isn't clear at first, I'll show you guys why we do this. So we do x times y minus 9 minus 9y plus negative 9 times negative 9 is 81. And if we add something to the left-hand side of the equation, we have to add it to the right-hand side of the equation. This is 81 as well. So now we can factor out the y minus 9 from this expression. So this is just x times y minus 9 minus 9 times y minus 9 is equal to 81. So as you can see, the reason we added the 81 was to make this, or let me make this a bit neater, there we go, is in order to make this more factorable, in order to get this y minus 9 term. So basically what you want to do in order to reach this is to multiply the coefficient of the negative 9y, which is the negative 9, by the term that we want to multiply it with, which is the negative 9 here. So we multiply those two, and that's just the 81 on the right-hand side. So therefore, we can factor out the y minus 9 from these two terms once again to get y minus 9 times x minus 9 is equal to 81. So as you can see, both of these terms had a y minus 9. So we just took the y minus 9 out. It's like factoring one individual variable, but instead of one individual variable, we factor out an entire, I guess, expression. So hopefully that wasn't too confusing. So now that we're here, we know that since x and y are both integers as given in the problem, we're going to want to find integer solutions of them, which means that we can simply guess and check different factors of 81 in order to make it work. So for example, this y minus 9 could be equal to 1 and this x minus 9 could be equal to 81. And when you multiply them both, they'll give us 81, which is what we want. And then something else we could try is if we do y minus 9 is equal to 3 and then x minus 9 is 27. This would also give us two numbers that multiply to 81. So listing the remaining, I guess, factorings of 81, we have 9, 9, and then we can reverse them. You get 27, 3, 81, and 1. And then we could also do stuff like -1 and -81, but we have to notice that the problem asks us for positive values of x and y. So therefore, if we have -1 and -81, the resulting value of x and y, one of them would not be positive. So like, for example, in this case, y would have to equal 8 because 8 minus 9 is equal to -1, but x would have to be -72, and that wouldn't work. So therefore, we restrict ourselves to positive values of y minus 9 and x minus 9. The closest that we would get is if we had -9, -9, and that would give x and y both equal to 0, but those would also not work since they're not positive. So solving each of these is pretty simple, or straightforward, since we have y minus 9 is equal to 1, so y is just 10. And x minus 9 is 81, well, that just means x is equal to 90. And basically, we can just go down, y is equal to 12, x is equal to 36, y is equal to 18, x is equal to 18, y is equal to 36, x is equal to 12, y is equal to 90, x is equal to 10. So all of these will give us, or all of these are solutions which will give us values such that 1 over x plus 1 over y is equal to 1 over 9. So these are our solutions. So that wasn't too bad. We just took advantage of Simon's favorite factoring trick in order to make x and y easily guessable, since we have this 81 here, which can be split into a finite number of factor pairs. So we can try a slightly harder example now, which we have to use SFFT a little more creatively in order to make it work. So let's try this problem. This problem looks a little intimidating at first, since we have all of these x squareds and y squareds. But what we do here is we notice that the x and y, or the x squared and y squared, can simply be substituted. So here we're going to let a is equal to x squared, and then b is equal to y squared. So this will make it so that we have the same format of equation as before. So this makes the problem b plus 3ab is equal to 30a plus 517. And basically, once you make this substitution, the rest of the problem is really easy. Let's move the 30a to the left-hand side. So we get 3ab minus 30a plus b is equal to 517. We're going to leave the 517 on the right-hand side because it's not really necessary for us to complete the factorization. So if we notice, or if we take a look at the first two terms, the 3ab and the -30a, we notice that what they have in common is 3a. So we're just going to go ahead and factor that out. Get that 3a times b minus 10a. And then we have, or not minus 10a, it's just minus 10. Oops. We have that. And then what we have left is just 1b is equal to 517. So now, in order to make this work, we want this b right here to also have a b minus 10 term. So this is a bit simpler than the previous question actually, because we can just subtract 10 from both sides in order to make this work. So we just have 3a times b minus 10 plus b minus 10 is equal to 517 minus 10. So once again, we notice that since we subtract 10 from one side, we have to subtract 10 from the other side as well. So this lets us factor out the b minus 10. So we just have b minus 10 times 3a, and the number of b minus 10s here is just 1, so we have plus 1 is equal to 507. Now, what comes after here is just obviously guessing and checking the factors of 507 in order to make it actually work. However, we have to realize that, or not we have to, but we realize that there is a shorter solution to this. So first we have to realize that 507 is equal to, this is equal to 3 times 13 times 13. And that's important because that means most of the factors of 507 are going to be multiples of 3. The only ones that aren't are going to be 1, 13, and 169, which is 13 squared. And the rest are all going to be multiples of 3. And the reason that this is important is because this term right here, 3a plus 1, this can never be a multiple of 3. And the reason for that is because when we have 3 times a, that makes the number a multiple of 3. And when you add 1 to a multiple of 3, it is no longer a multiple of 3, no matter what a is. You can try this with any value of a, that is an integer, that is. And our values have to be integers because remember that a is equal to x squared. And if x is an integer, x squared is also an integer. So no matter what value of a we have, 3a plus 1 is not going to be a multiple of 3. So therefore, 3a plus 1 can only take on a few different values, actually. It can take on 1, it can take on 13, it can take on 169. So we can try these different, we can try each of these and see what it gives us for b. So if 3a plus 1 is equal to 1, that means b minus 10 has to be 507. If 3a plus 1 is 13, that means b minus 10 has to be 39. And if 3a plus 1 is 169, that means b minus 10 has to be 3. And so this gives us 3 different values for b. This first case gives us, or move the paper over. This case will give us that b is equal to 517. And since this is b is ultimately equal to y squared, since we have to remember the substitution that we did at the very beginning, right here. Oops, I didn't mean to erase that. This substitution right here. We realize that b cannot be 517 since this is not equal to any, since there's no positive integer, or there's no integer value of y such that y squared is equal to 517. So that's simple enough. Now we take this value 39. This will give us b is equal to 49. If b minus 10 is 39, then b is equal to 49. And if this is equal to y squared, then that means obviously y is equal to 7. It could also equal negative 7 as well, but it doesn't matter since the problem ultimately asks us to find 3x squared times y squared. And square root of 7 or negative 7 is the same. So for simplicity's sake, we'll just say it's equal to 7. And then we have this last one, 3. So that means if b minus 10 is equal to 3, then b is equal to 13. And if this is y squared, it's not going to work as well. So therefore, the only solution we have is if y is equal to 7. And that means we can find the value of x, corresponding value of x that works as well. So the value of 3a plus 1 that worked was 13. So if 3a plus 1 is equal to 13, and that means a is equal to 4. And since a is equal to x squared, x is equal to 2. So therefore, our final solution is just xy is equal to 2, 7. And if we plug this back in to 3x squared y squared, which is what the problem wants us to find, this is equal to 3 times 4 times 49, which is equal to 588. And this is going to be our final answer. Okay. So we actually solved this one pretty easily as well. We just had to notice that it required a very important substitution at the beginning, which is this a is equal to x squared and b is equal to y squared at the top. And once we use that, it just becomes a normal Simon's favorite factoring trick problem like the last one. So we're actually finished with the handout a bit early. So let's try one of the extra problems that we have here. Here's a list of the problems that we have on the handout. Yeah, this is just a taken screenshot, which is why it looks a bit messy. We can try any one of these. I personally like number 4 since, oops, how do you zoom in? There we go. I like number 4 since I like d equals rt problems. So let's go ahead and solve that one. So let's see, how do I do this? I don't know how to crop this, so let's just circle this one. Number 4. So I'll give you guys a second to read it. Okay, so the problem gives us 3 different people, Han, Ian, and Jan. And then we're given the difference in their speeds. Their speeds as well as their times. And then we're also given one difference in distance at the end as well. So that should tell us why this is a d equals rt problem to begin with. So since everyone is comparing their speeds in such to Ian, let's set Ian to be the variables. So Ian. So let's actually make a chart. We can have speed here. Oh my God, why is this? There we go, speed, and then time. So let Ian's speed be s, and let the amount of time that he drives be t. So it states that Han drove 1 hour longer. Hello? I can't cross my H for some reason. Okay, whatever, that's Han. So it states that Han drove 1 hour longer than, so this is t plus 1. And he drove at an average speed of 5 miles faster than Ian. So the speed is going to be s plus 5. And the problem states that Jan drove 2 hours longer than Ian. So this is t plus 2. And then the speed at which Jan drove was 10 miles per hour faster. So this is s plus 10. So now we have 3 different speeds in 3 different times. And the final piece of information that the problem gives us is that Han drove 70 miles more than Ian. And then it asks us how many miles did Jan drive than Ian. So in order to calculate the amount of miles each of them drove, we use d is equal to rt. So if this is equal to speed is rate, which is to r, t is the time, which is equal to t, then d, distance, is just equal to r times t. So for Ian, the distance he drove should be st. The distance that Han drives should be s plus 5 times t plus 1. And then the distance that Jan drives should be s plus 10 times t plus 2. Oops, let me move it over a bit. t plus 2. So it then tells us that the distance from, or sorry, the difference in distance that, the difference in distance that Han drives is 70 miles more than Ian. So that means Han's distance, which is s plus 5 plus 5, s plus 5 times t plus 1. And then we subtract Ian's distance, which is st. This is equal to 70. Okay, well, that just means that if we expand this out, this is st plus 5t plus s plus 10 minus st is equal to 70. So this just gives us 5t plus s is equal to 60. So now we want to find the difference in distance that Jan drives more than Ian. So that just means we have to calculate s plus 10 times t minus 2, or t plus 2 minus st. So this expression is equivalent to st plus 10t plus 2s plus 20 minus st. The st's cancel out. And we already know that 10t plus 2s is equal to 120. So if we multiply this, or we know that because if we multiply this by 2, we get that 10t plus 2s is equal to 120. So if we plug this in here, this gives us 120 plus 20 is equal to 140. And that is our final answer. So yeah, that was just another d equals rt problem, which demonstrates that what we have to do, or this one's a bit different, in which we had to manipulate the equations a little bit. We didn't explicitly solve for s or p. What we did here was just use creative substitutions in order to make it work for us. So yeah, I think that's all we have for equations today. I think, yeah, if you have any questions, you can now direct them to me or Justin, considering I'm done lecturing. And next week we'll be going over quadratics and polynomials and factoring and all that. So we can talk about Vieta's, Sophie-Germain, probably rational root theorem, maybe graphing, and all of that fun stuff. So if you don't have any more questions, you're now free to leave, I guess. Thanks for joining us.
Asking if there is a mistake in the...
Quite possibly. I am very error prone.
Yeah, they claim the answer is 150, so...
Did I do something wrong? Okay. Oops. Let me zoom out.
I get one comment, the 10 is a 5.
Oh yeah, here. I see what I did wrong. This is 5 times 1. So this is just 5. And this should be 65 then. This is 130. And this is 130. So yeah, that was my bad. I multiplied 1 by 5 and I got 10 somehow.
For people asking about the handouts, we will release that in a few days.
Yeah, the handouts will be posted. And also the recording will be posted as well if you want to go over any of this.
Which I will end now.
Okay.